Greetings, everyone. My name is Rick Blakely. I'm the president of the Geomagnetism and Paleomagnetism section, and I'd like to introduce my friend and colleague, Richard Gordon, who's the president-elect. And it's our great honor to introduce to you our 2011 Bullard lecturer, David Dunlop. You might wonder why it takes two burly, some would say slightly overweight people to chaperone a somewhat diminutive man, but it's because of the sheer scientific stature of this guy. I found it difficult to believe when I learned that Dave had not already been a Bullard lecturer, and I think you will agree this is a slam dunk selection. Dave received his PhD from the University of Toronto in 1968. He then occupied postdoctoral positions, first at the University of Toronto and then the University of Paris. He landed back at the University of Toronto in 1978, where he has remained ever since and is currently Professor Emeritus. But don't get the opinion that Dave is a homebody. Quite to the contrary, Dave has been a researcher, lecturer, or visiting scientist at universities and institutions in the United States, England, Russia, Japan, Germany, Australia, and France. Dave has received the Medal for Achievement in Physics from the Canadian Association of Physicists, the Bancroft Award from the Royal Society of Canada, the Lewis Nail Medal from the European Geophysical Society, and the J. Tuzo Wilson Medal from the Canadian Geophysical Union. He's a fellow of the American Geophysical Union, a fellow of the Royal Society of Canada, and he's also a former president of this section. Dave has published well over 200 peer-reviewed articles ranging in subjects from rock magnetism to paleomagnetism to crustal magnetic anomalies. Three separate publications of his have received more than 200 citations each. This one last picture, I particularly like this picture. It shows Dave and Ozdemir standing on a cliff somewhere in the Rocky Mountains. If you look very closely, you'll see that Dave is leaning against Ozdemir as if he's afraid he's going to fall over the edge. And I'll conclude with just a short little story that involves Alan Cox, a discussion between Alan Cox and David Dunlop. This took place in an AGU meeting way back in the mists of time. I've heard this story so many times, I feel like I must have been there. This was when the AGU meeting was in the Jack Tar Hotel on Van Ness Avenue, when I suppose the entire meeting wasn't too much larger than the people in this room. Alan had a student who was giving a presentation, and it may have been his last presentation. At the end of the question and answer, or at the end of the talk, the question and answer period, the student was asked by someone in the audience, have you done any rock magnetism? The talk was about paleomagnetism. Have you done any rock magnetism, any rock magnetic experiments? The student quickly replied that he hadn't bothered with any of that because Alan always says that one paleomagnetic study is worth two rock magnetic studies. Well, Alan turned to Dave and apologized, but Dave had the perfect comeback. He said, "Never mind, Alan, I have plenty of reprints to spare. I can afford to exchange two of mine for one of yours." So Dave's talk today will be rock magnetism, successes, and mysteries. And so without further conversation, please join me in welcoming our 2011 Bullard lecturer, David Dunlop.
Well, thank you, Rick. So, rock magnetism, successes and mysteries. I'd like to start with a light pointer here. Here we are. I'd like to start by remembering some of our past. We have a very distinguished past in rock magnetism. It was around before there really was any paleomagnetism and paleointensity. I'll show some of the applications, some perhaps less familiar applications of rock magnetism for most people, to paleothermometry and depth of burial, the question of how Mars' magnetic crust managed to survive with no field around for 4 billion years, and the question of deep sources of magnetic anomalies, where they might come from. Then finishing off with some mysteries and surprises, where does stable TRM come from anyway? Something that we certainly should know 60 years after Néel, but in fact we don't seem to know that. And why is it that we cannot see the domain structures that are responsible for the success of paleomagnetism? Who invented rock magnetism? Well, it certainly wasn't me, nor was it my friend and fellow Torontonian, Bob Carmichael. It was the man in the middle here. It was Telly Nagata, who's shown here back in 1968 at the University of Tokyo, the old master of our field. He wrote the books that defined the subject. But who really invented rock magnetism? Well, Louis Néel was the one who provided the physical rationale for TRM. And certainly without Néel's demonstration that TRM is stable essentially forever, who would ever have put their faith in paleomagnetic reconstructions or in magnetic stripes and seafloor spreading? But we might ask again, who really invented rock magnetism? And I guess the answer would be that the ultimate architect of rock magnetism was Émile Tillier, who labored throughout the 1930s establishing these wonderful laws of additivity, independence, and reciprocity of partial TRMs. Not just wonderful on their own account, amazing in an earth science subject. There are very few parts of physics that have such neat laws. But without his demonstration that TRM is built up from a series of partial TRMs, all independent of each other, Néel would not have been led to associate these partial TRMs with ensembles of single-domain grains. Well, surely that's established the origins of the subject, but not quite, because when we look at the Tillier A Protocol for doing paleointensity determination, we find, my gosh, that was invented by Königsberger rather than Tillier. Not that he used it for paleointensity, but his procedure was to start with a total TRM, or in the case of a rock with NRM, then carry out double-step heatings to a set of increasing temperatures, here, 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 in reversed fields. So each step, he reversed the field. Then, this is the Tillier Protocol, then one can analyze the data, although Königsberger didn't do this, but you can easily analyze it in the way that we do today by taking the half sum of the two curves, which gives you the TRM remaining, or the half difference, which gives you the PTRM that's been gained. So that was around already in 1938. Nowadays, of course, we tend to plot things in the Araya diagram, which was an invention of Nagata's group. So combining the data from the first slide, from the two curves, and plotting them on two separate axes as TRM remaining versus partial TRM gained, we get this somewhat sagging Araya plot. Not surprising, because these are very much larger than single-domain grains, but it's a fairly simple, nice-looking graph. But then when you look at a magnetite ore, you find that nature can be a whole lot more complicated than that. The ore contains both pyrrhotite and magnetite, and these things clearly interact negatively. You get an increase in TRM when you heat in zero field between 400 and 500. So something very strange is going on there. Anyone who's worked with lunar rocks has seen things like this when tetrataenide is in the rocks. It was often said that Telly and Nagata never spoke to each other. Well, that's clearly not so. Here they are, shoulder to shoulder, receiving honorary degrees in Newcastle upon Tyne, also back in 1968. Over the 20 years between 1937 and 1959, Émile and Odette Tellier invented paleointensity determination. And I note in passing that Tellier was not worried by his early results showing that the Earth's field had decreased by more than 30% in the preceding 19 centuries, and to add to that, a further 20% in the 8 centuries before that. That, as you can imagine, was at the time a very controversial result. But again in passing, that led directly to the idea that carbon-14 ages needed to be corrected. Nowadays, we wouldn't imagine using a carbon-14 age that had not been corrected, but that very idea didn't exist at the time. The first practical paleointensity technique appeared in this paper by Roquet and Tellier in 1946. It's very close to the Tellier approach, except that 2 separate experiments were done. First, they measured zero field demagnetization of a TRM. Then, in a separate experiment, the blue points, they measured in the same temperature steps the buildup of partial TRM. To compare the data from the 2 experiments, they flipped one of the curves over, in this case the red curve, rescaled it appropriately, and matched the 2 curves point by point, which, if they do match, shows you that the NRM is a TRM over the appropriate range of temperature, and also it gives you your paleointensity from the rescaling factor. This is what I call a Roquet plot because it first appeared in this paper. When you plot up the Roquet and Tellier data for hematite on an Araya plot, you get this absolutely beautiful single domain plot. Notice that almost all the blocking temperatures are very high above the Curie point of magnetite. Wanted to show a few examples taken from Tillier and Tellier in 1959, their classic paper, which show the effects of thermal overprinting of the TRM. This one's from the Terme de Cluny in Paris. And when you do the Roquet procedure, you see that the 2 curves match beautifully from 180 degrees upwards, but not below. Hello. Let's get back. But not below 180 degrees. And the reason for that, you see it in the Araya plot as well, is that they had a building fire, which reheated these bricks up to that temperature. So if you know the event that happened, you can predict or determine what the temperature was that caused it. That's paleothermometry. Another example a little bit earlier in time from Carthage. Here there's a match of the curves above about 200 degrees. Notice it's much more obvious where the mismatch is in the Roquet plot than it is in the Araya plot. So what was the event that caused this thermal overprinting? These are sacrificial urns, and it's rather a grisly story. These were human sacrifices. They were cooked, and the red-hot bones were then thrown into these urns to cool, thereby heating them up to about 200 degrees. I'm glad I wasn't around at the time. A less grisly example, comparing Roman wall and floor tiles. The wall tiles were never heated again since the time they were originally fired, But of course, the hearth floor tiles were reheated many times, cooking meals for the legions. And you can tell just how hot that hearth floor got, about 350 degrees. And I just had to show this one because it has nice scenery, for one thing, from the Massif Central, but also because it's often said that the teljes never looked at volcanic rocks. Well, that's not true. They just didn't often have successful results from volcanic rocks. But this one was an andesite rather than a basalt, and it worked just beautifully. Of course, Tillier's crowning achievement were the laws of partial TRM. In 1946, he gave this very clear statement. They were restated over the years many different times, but this is the statement that is the clearest. To any interval T1, T2 is linked a thermomagnetic moment acquired during field cooling from T2 to T1. This moment is unaffected by heating to T1, but vanishes completely by heating to T2. So what was put in between T2 and T1 completely comes out between T1 and T2. That's reciprocity. The moment is independent of moments acquired in intervals outside T1, T2. Law of independence. All the moments add vectorially, the law of additivity, yet each of them retains a genuine autonomy and an exact memory of the temperatures and fields which created them. We use that memory of the field, of course, every day in paleomagnetism and paleointensity work. We rather seldom use the memory of temperatures, and that's more what I want to concentrate on today, magnetic paleothermometry. Néel came on the stage in 1949. He had just done his Nobel Prize-winning work, published in 1948, and he needed a little change of pace. Here he is pondering the problem of what's causing these interesting laws of partial TRM. He came to the correct conclusion that each grain has a relaxation time, each single domain grain, which depends on its volume, V, and its coercive force, and on temperature T in this combination. So during cooling, when the relaxation time increases, which it does very rapidly because of the exponential function, when you reach a relaxation time that's equal to the time of your experiment, TRM is blocked in very permanently. That's the blocking temperature. If you later demagnetize by heating up in zero field, then the grain will demagnetize at exactly the same unblocking temperature. So there is Tellier's law of reciprocity explained. Now, each grain has a sharp value of the blocking temperature, but it's shared by all the other grain ensembles that have the same value of this product, VHC, because that's the combination that occurs in the equation for relaxation time. Néel then invented this useful diagram of volume versus coercive force, in which all ensembles with the same value of VHC, and therefore the same blocking temperature, are linked together along this hyperbola. Change the temperature, and the hyperbola moves through the grain distribution of all ensembles, either magnetizing or demagnetizing the grains. If you turn the field on just between 400 and 500, you'll magnetize everything in this strip. Between 500 and 550 in this strip, the two strips don't overlap. Their magnetizations don't know about each other. They don't care if you change the field direction in between. They are independent and they are additive. Néel did not continue on to produce this diagram, although he could easily have done so, because time and temperature are equivalent in his theory, so that a change in temperature T or in log of F naught times time have exactly the same effect in the equations. So Palaya et al. Plotted things on a diagram of time versus temperature, and these curves correspond to a single ensemble. They allow you to predict what combinations of time and temperature will magnetize and then demagnetize this ensemble. So to take a concrete example, suppose that you produce a VRM at this temperature for single domain grains, which in fact is what we did. The temperature, I think, is about 280 degrees. And we did the experiment for a few hours, so that's how we got this point. Then heating fairly rapidly on a time scale of a minute or two, you could ask the question, how high do you have to heat in temperature in zero field to get rid of this VRM? Well, the experimental answer is up to about 320 degrees, and that is exactly what these Palaya contours, or nail theory, predicts. So if you stick to single domain grains, here's another example with green data, or over a much longer term, the Milton monzonite of Australia, magnetized on a 100,000-year time scale, demagnetized in 10-minute experiments at considerably higher temperatures. Everything is beautiful. It follows these curves. When you look at larger grains, however, 20 micron grains, 135 micron grains, or at non-single domain samples from rocks, then you get results that cut sharply across these theoretical contours. You have to go to much higher temperatures. A thermal demagnetization tail, not predicted by nail theory. Well, I'd like to consider an example of paleothermometry from the Sydney Basin, from the Milton monzonite. The first task, well, first of all, you want to be sure that you're dealing with single domain material, because otherwise it isn't going to work. But your next task is to identify the temperature to which things were reheated. And you do that by looking for the intersection between the overprint trajectory on a vector diagram in space and the primary TRM, which is this high temperature component. If you do this for two different minerals, here it's pyrrhotite and magnetite, then by using the different Palaya contours for those two minerals, for pyrrhotite, we had a remagnetization temperature of about 200 degrees. We follow up that contour. For magnetite, the remagnetization temperatures were a bit over 300 degrees. We go up the magnetite contours, and where they intersect gives us a prediction that the time of remagnetization was 100,000 years, with, of course, a fair amount of slop in that. But the remagnetization temperature is more tightly determined at 165 degrees C, plus or minus about 30 degrees. And happily for us, this did agree with conventional estimates from vitrinite reflectance. And these are important for the issue of maturation of coal. How good quality is the coal that you get by digging down in the Sydney Basin? So it is quite a practical result. Another much larger scale example of magnetic paleothermometry concerns these magnetic anomalies in the southern hemisphere, the southern highlands of Mars. They are not only very intense, about 10 times anything that we see on Earth, they also have survived for an incredible length of time, 4 billion years in zero field. The field on Mars that produced the anomalies died 4 billion years ago. So a couple of questions that we might interrogate the Palaya curves about. First, we need to magnetize the entire Martian crust, because to explain intense anomalies, you need as thick a source as you can get. So it takes time to magnetize the entire crust in a blocking temperature range of about 500 to 550 degrees, assuming magnetite as the mineral involved. We think of blocking temperatures as being sharp, but they're not completely sharp. In going from 5% blocking to 95% blocking, you have to cool through a certain temperature range, which in the high temperature part of this diagram is about 5 degrees. Well, if you know the cooling rate, and we're guessing that it's half a degree C per million years, pretty slow, that takes 10 million years just to get through one of the blocking temperatures of one of these ensembles. You have to cover the whole range from 550 to 500. That 50-degree range takes you about 100 million years of cooling from the top to the bottom of the crust. So Mars' dynamo has to survive for about 110 million years, which doesn't sound too difficult. Surely if we can produce the dynamo, we can make it last for that long. But the more penetrating question is, after Mars' field died, could the TRM of this crust have survived for another 4 billion years with no field to support it? Why didn't it just viscously decay away? Well, to preserve it, you have to do some further cooling of the crust. You can't just leave it at 500 degrees. You have to cool it, picking on 500 as the most vulnerable grains to remagnetization. Let's follow the contour up to 4 billion years, which is just a little bit off the diagram, but it's around 400 degrees. You have to cool another 100 degrees to stabilize those particles, we predict, for another 4 billion years. And that takes you another 200 million years. So now the ante has been raised. We need a dynamo that will last for 300 million years, not 100 million years. Very simple diagram here with rather powerful predictive value. The Earth, too, has its regions of long wavelength anomalies, which seem to require, at least in part, deep sources. One of these regions is the Kapuskasing uplift in northeastern Ontario. And here I am with a field companion out on a nice summer's day on the Canadian Shield looking for rocks. Well, there are lots of rocks right under our feet, but we're looking, of course, for the right rocks. This is the Kapuskasing structure. It's an uplift structure which has brought middle and perhaps a little bit of the lower crust to the surface. It's outlined on the magnetic anomalies map fairly clearly, and some of these anomalies are substantial, although, of course, these anomalies are determined by flight lines that are 300 meters above the terrain, not 100 or 200 kilometers, as with the Martian anomalies. So they're big, but not Mars big. So what do we find on the ground in these rocks? We find that even the most magnetic rock type, the tonalite gneiss, is not up in the right range, which is about 1 amp per meter and above, if you want to explain the anomalies. Most of this histogram, you can see, is well below those levels. And when you look at all the different rock types plotted here on this diagram that I like very much of NRM versus induced magnetization with the Königsberger ratio Q as a parameter, so that roughly speaking, everything above the middle line is remnants dominated, everything below is dominated by induced magnetization. The samples that would explain the anomalies are just up in this corner here, and there are very few of them. So the things we are seeing at the surface, which, remember, came from depth originally, so they are representative at least of some of the deep rocks, they don't have enough magnetization. Where is the missing magnetization? Well, part of it may actually be due to the physics of the situation. When the temperature rises, single domain grains unblock, therefore the Q goes down, the NRM contribution goes down, But the induced magnetization, the initial susceptibility, it goes up. Another effect is that the thermoviscous magnetization, what you get by simply applying the field for a very long time, it also goes up, and that's another effect that may also be very important. But just to stick to the enhancement of susceptibility, that is not just a property of single-domain grains. These data haven't actually appeared in print yet, but I'm very fond of them, and I will publish them fairly soon. You can see that the Hopkinson peak, as it's called, in susceptibility, already for 14 micron magnetites is about 125%. 25% above the room temperature level, 150% for 1 micron magnetites, and over 200% for half micron magnetite, which is still way above the single domain size of magnetite, which is 0.1 micron or even a bit smaller than that. In terms of volumes, it's orders of magnitude above the single domain volume. You know, it's like comparing the size of a chair here to the size of the room or the size of the building. These are huge discrepancies in size. If you are trying to understand why does the building have the properties that only a chair should have, these are big differences in volume, just to emphasize that. This is one aspect of what's come to be known as the pseudo-single domain, or PSD effect. Great big things can behave, can mimic little tiny things. So that's the end of the successes I want to talk about. Now I'll go into the mysteries. And this is an enduring mystery. When I was a beginning graduate student, my supervisor drew on the back of an envelope in proper supervisor fashion these two little pictures here. One was a single domain grain, and he said, this is strong and stable. The other was a two domain grain, and he said, just by putting one domain wall in, and it can move around, suddenly the stability and the intensity are gone. And then he scratched his head and said, I wonder what happens in between. That was a very good question. I thought I could solve that by the end of my PhD, but it hasn't turned out that way. I still don't know the answer. I hope someone finds out. I had to, of course, show a day plot, and even if you don't know what a day plot is, that doesn't matter. I like day plots. And in this upper corner here should be all the single domain grains, because they're very magnetically strong. Down at the bottom where things get weak, that's where the two domain, three domain, multi-domain things should live. And in between should be a no man's or no particles land. Nothing should land there. But of course, what we find, I was looking around in the posters in the hall today at all the day plots that were there, and every single one of them had all of the magnetite points in the middle between the two. That's where they all live. So we have a serious problem here, that instead of an empty region, the reality is that typical paleomagnetic samples have these intermediate properties. Frank Stacey knew about this back in the 1960s. He was the one who coined the term PSD. And shortly after, Lynn Perry showed that magnetites as large as 20 microns could mimic single domain behavior. They were also PSD. So what causes these big grains to mimic single domain behavior? Well, if you go looking for classic domain structures by polishing very carefully a 110 surface of magnetite, and Usden does this magnificently, which is why these pictures here are better than anything you can find in a textbook on domain structures. These show not just spike domains, reverse spike domains, they show spikes upon the spike domains. They show perfectly developed 79 and 109 degree walls, and also lovely 180 degree walls between the body domains. Everything is there, just as Landau and Lifshitz showed in their paper. If you look at the very small end of things, which Dunn and Porkowski et al. Have done here using electron holography, at single domain particles, you can find those too. These magnetosomes are individually single domain. They're also linked together, flux linked along a chain to produce an elongated single domain particle. They're out there in nature, but if you just go at random and pick up your average kind of dirty magnetite from dirty old rocks that we do paleomagnetism on, you find something considerably messier. And I think Usden and I are just as proud of these results as we are of the textbook examples. They show that domains in natural magnetite, these are inclusions in biotites, do strange things. The walls bend, which they shouldn't do. Magnetostatics says they can't do that in a strongly magnetic material, but they do. They're anchored strongly by defects and cracks. This wall is bending, this wall is pinned at a defect. The walls here are so strongly affected by the crack that even by applying large fields, they don't move. The ones that are loosely pinned, they move easily. Maybe it's the complexity of the real world, the real magnetites, that produces single domain-like behavior. Another very clever idea, when domains fail to nucleate for whatever reason, we can get single domain behavior metastably. Hagedal and Fuller's original diagram here of a quite large titanomagnetite grain shows something that is single domain. It's been saturated in a strong field, but it doesn't remain single domain for long. If you put a small reverse field in, here's a domain nucleating, and then the wall sweeps rapidly across the particle and reverses the moment. In a different experiment, by simply replicating TRMs, sometimes you get different numbers of domains, including, occasionally, single domain states. The trouble, though, is that these things would have to last for geological time, and that seems rather unlikely because it's just too easy to renucleate these domains. They have strong magnetism, but they do not have very stable magnetism. An idea that I was very fond of in the early days turns on the fact that a 180-degree domain wall itself has a magnetic moment. The two body domains are horizontally magnetized here. The domain wall has a net moment which is up, or equally well could be down. There are two magnetic states, just as Néel prescribed for a single domain grain. You can transform from one to the other by an exotic process, block line propagation. And the wall moments and the domain moments are orthogonal to each other and therefore independent. So these wall moments act like canonical single domain grains. I called these psarks because at the time I wanted to do something that sounded like real physics, so I imitated quarks. And people in my physics department were really quite impressed by this. And it's hard to impress people in a physics department, especially if you're on the wrong side of the H-bar gap. Now, the trouble with these things, I forgot to say what the fatal flaw is in all this. The trouble is that the different wall moments interact with each other. So it works fine if you have just one wall moment. If you put in two, they line up in the opposite direction to form a closed flux loop. And therefore, a typical multi-domain grain will have practically no moment. I thought I'd solved the problem, and not at all. It all slipped away. Well, this effect of interacting neighbors has been shown beautifully in AFM and MFM images taken by Josh Feinberg and Gary Scott and colleagues. These are not separate domains, but along this band here we have neighboring single domain magnetite prisms, which are separated from each other by non-magnetic or practically non-magnetic Alva Spinel. And in the MFM image, you can see that the colors go white, black, white, black, white, black, white, black. These are left magnetization, right magnetization, left, right, left, right. They alternate You can weave your way through them in a flux pattern. They like to close their flux. The net moment, unfortunately, is very small. The most amazing images to me of all are these electron holographic images produced by Richard Harrison and his colleagues. I just love this pair of pictures. Here we have 4 single-domain particles whose flux is linked together end to end, like putting together 4 compass needles, and you know what they'll do? They'll line themselves up. If you put 3 compass needles side by side, they will alternate in polarity, and that's exactly what these particles do, closing their flux in part with these 2 little flux loops here and here. On the right-hand side, notice the scale bar right on the single-domain size for magnetite. Here are some classic single-domain particles with flux lines continuing uniformly through the particle, and then on the right-hand edge, 2 vortex structures with internal flux closure, and an even more amazing thing to discover, what I call a supervortex, which links together these 3 neighboring particles. So it has it both ways, compass needles lined up end to end and side by side. Well, the bad news, of course, in there is that these vortices are not very good for paleomagnetism because they hardly have any magnetic moment. Very hard to produce a high-intensity TRM if you start with something with these small moments. Well, all magnetic properties, TRM, other remnants of stability, coercivity, susceptibility, we saw a few minutes ago, seem to change continuously between the magnetite single domain size and the upper PSD limit at 20 microns or so. So instead of the step-like change that one would expect between single domain properties and, say, the vortex state, instead we get a broad blend zone with continuous variation of properties. So what is the bridging structure, the domain structure that allows us to continuously change the magnetic properties between single domain and multi-domain? Question mark is there because I don't think we know. The other possibility, and people like to mix together things these days, mixing curves are all the rage, maybe there is a simple answer that there's a single domain fraction which is somehow sprinkled in with all different grain sizes, obviously in different proportions, less of it as the grain size gets larger. If that's the case, this is the vital impurity, the magnetic impurity that makes paleomagnetism work. I think we really have to worry about this question of what goes on in this grain size range of magnetite where so many of our samples fall, because without it, we wouldn't have paleomagnetism and we wouldn't even know about seafloor spreading. We've had these ideas around so long, we know now that plate tectonics works, so we've almost stopped caring about why it is that paleomagnetism can record things so stably. Anyway, I didn't manage to solve it as a graduate student, nor in the years since. So to the younger people in the audience in particular, I pass on the torch. Please don't forget about this question. It's absolutely vital. To conclude, the greats of our field, we were so lucky that we had these people on the scene in the early days. Remember that they were laboring at the time of the Second World War in Japan and France, not good places to be working in the Second World War. As both Nagata and Tellier told me at first hand. So Tillier contributed 2 decades of meticulous experimental work and his laws of partial TRM. Nayal produced an unassailable theoretical base that we could trust and build on. Nagata and Nagata's brilliant students, with some of whom I had the honor to work, broadened out the subject and they made it accessible to the whole world through their books. In applications, temperature T and time little t are linked in TRM blocking, allowing us to do magnetic paleothermometry. If you have two minerals with different time temperature contours, you can determine simultaneously times and temperatures of burial. Looking on a big scale at a planet-sized question, we can make predictions about how long Mars' field must have endured and how much cooling would have been required for its crust before the field turned off in order to stabilize that TRM until the present day. Crustal magnetic anomalies on Earth, and for that matter, on other planets, require at least some deep sources. And I've always felt that a partial source could be simply the enhanced induced magnetization at high temperature. It's significant not just for single domain grains, but for grains as large as 10 or 20 microns. And finally, magnetic force microscopy and electron holography, these marvelous new techniques. Not entirely new, of course, because I see Ted Evans in the audience, who a long time ago was using electron microscopy to show that there were single domain grains in at least some rocks. But these very sophisticated applications that we have today have really clarified what is going on in the single domain transition region. But the trouble is, it's so hard to push that to the larger grain sizes. The burning question that remains for paleomagnetism in my mind is what causes PSD intensity and stability of remnants in much larger natural magnetites? Thank you.
Before we go to questions and answers, have two orders of business. The first is I would like to present Dave with this certificate from the section and from AGU suitable for framing. There you go.
Thank you.
And the second is to remind you that at 6:30 we have the GP reception and business meeting. It's in the Intercontinental Hotel, ballroom C, I think. You'll find signs that will direct you, so don't forget that event. So what I would like to have you ask the question of Dave, and Dave, because they want to have it mic'd, he will repeat the question to you, and then hopefully he will answer it. Okay? So I'll just let you go ahead. Sure.
Okay, I got the first part of it. We've got Martian magnetic anomalies and reversals. That's a very good point. The question is how often during this 300 million year period might the field have reversed? Obviously, if it's similar to the terrestrial model, quite frequently. And in that situation, each time it reverses, that resets the clock. So it's really a much more demanding requirement than it at first seems. You need a field that endures at least in the same polarity, if not the same strength, but at least the same polarity for a very long time. If you don't have that, you may magnetize part of the crust, but not all of it. Or worse, you'll have alternating layers of the crust of opposite polarities, and then you have no magnetic source at all. Is there? I have the lights in my eyes, and it's very hard to tell. So maybe just stand up and.
Yeah, related question. I think Martian magnetization is outrageously strong compared to the terrestrial rocks of any kind known. What do you make of it? Do you have any suggestions or proposals for the origin of the Martian very strong magnetization?
The comment and question are that the Southern Highlands Martian anomalies seem to be outrageously intense compared to anything else that we know of in the solar system. Do I have any insights in this? Many people have made suggestions, but it's really very difficult to explain this. This is why we call into play the entire crust. It's just to try to get 30 or 40 kilometers of source material. Even then, we have to go to intensities of magnetization of something like 10 amperes per meter, which is like a fresh mid-ocean ridge basalt. But unlike MORB, this has to stay unchanged for a long period of time. No, I have no special insight. But they are there, outrageous or not.
If Susan McEnroe or Laurie Brown are in the audience, they might want to help me ask this question. Part of your explanation for deep crustal sources in the Earth is induced magnetization, but I believe we have some good evidence of reversely magnetized rocks at deep crustal depths, and I wondered if you could comment on that. It would require something besides induced magnetization.
Well, certainly I'd be the first to agree that induced magnetization is not the whole story of deep or shallow sources. The anomalies that Suzanne McEnroe and Laurie Brown have worked on, for example, in the Adirondacks and in Fennoscandia, have an entirely different source. I had slides in the talk on hematite and ilmenohematite. I took these out in the interests of finishing a bit more on time. But you can produce sort of an ideal magnetization source if you take hematite and then subdivide it on a very fine scale. The layers between these exolved minerals have remarkable properties. They produce a ferrimagnetism, which is not as strong as magnetites, but still a substantial fraction of that, coupled with a coercivity, a stability that is very much that of the mineral hematite. Hematite, of course, is weakly magnetic, but strongly coercive. And by conventional wisdom, these things should not produce anomalies. In fact, they do. So I think that's the source that you are referring to.
Yes.
The question is, when one uses low temperature demagnetization, which consists of cooling through the magnetite-Verwey transition in zero field and then returning to room temperature also in zero field, you erase a fraction of the remnants. The larger the grain size of magnetite, the larger the fraction that's erased, leaving you with a residual that has really very single-domain-like properties. In a quite old paper by Argyll and Dunlop, we showed that you can literally match these properties of the low temperature residual. Well, it's measured at room temperature, but it's what's left over after low temperature cycling. They really are indistinguishable from single domain properties. And that applies to grains which are really quite large. Certainly a micron and above, a few microns. Yes.
For the stability versus temperature curve that you're showing, the largest material you're using is 110 microns. What is the prediction of even larger materials that are opposite?
Okay, this concerns the time temperature contours. Oh, all right, susceptibility versus temperature. All right, I'm on the right.
So you showed here that the smaller grain size is the large teljes. How about the other say those are extreme large grains that what is
Yes. So the question concerns the Hopkinson peak in susceptibility and how it changes with grain size. I emphasize 14 micron, 1 micron, half a micron. But on there are also the data, which I guess we should be able to access. We lost, we fell out of the slideshow. Yeah, this is good.
From the beginning or the current slide? What do you want?
Current slide's probably better. Okay. Whoop, going the wrong way. Oh, wait a minute. I went past it. I must have gone past it. Here we are. Okay, that was a lot of work. So the answer when you go to larger grain sizes, you get the multi-domain flat plateau. So the first evidence of any sort of peak is around 14 microns. Richard? Okay, the question is, there is the high temperature Hopkinson peak, but also in these data, you always see a subsidiary lower temperature peak. No, that is due to the fact that these magnetites were not heat treated in advance. If you do this experiment a second time, that lower temperature peak goes away. It's due to stress. These are synthetic samples. The data, I should give credit where credit's due. The data were measured at the IRM. And you know, time is precious, so I didn't do double heatings. I just did it once. And for a few of them, I checked. It goes away. Yes? They look very similar. Not identical, but very similar. They're close to reversible. Of course, as the grain size gets smaller, you can't really control the atmosphere in the Bardington Bridge that was used to get these data. So there is some oxidation of the magnetite, so that the peak height does drop somewhat for the smaller grains. The shape of the curve, however, does not change.
I think we've hung Dave out to dry long enough. Let's call this meeting to a conclusion, and let's have one last loud thank you for Dave Dunlop's nice presentation.